Hey there, welcome back to 2241. Today we're going to talk about lines and planes and how to write equations for them. All right, so let's go ahead and get started with our terms and formulas as usual. All right, so our terms here are lots of equations. We have vector equations for lines and planes. We're going to learn what a parameter is. We have parametric equations for lines and planes. We'll learn what direction numbers are. We'll also learn what a symmetric equation is for a line and a convex equation for a line. And we'll also learn what a normal vector is. We sort of already know what that is, but we'll learn it more generality. A scalar equation for a plane and a linear equation for a plane. Both of those are fairly similar. All right, so moving on to our formulas here. We're going to start with all of the equations for lines. Now, we have the vector equation, which is probably the simplest to write down. And it looks like this. We have any point on the line is represented by a starting point plus some scaling parameter times the vector going in the direction of the line, or a vector going in the direction. And those are usually written this way. So R0 and V. Next up, we have the parametric equation of the line. And this is basically the vector equation, but split up into its components along the x, y, and z directions. Here we have symmetric equations. They look like this. And then convex equations for lines look like this. We'll see why those look like that in a minute. Next up, we have surfaces. So these are usually planes. I guess I should have written planes there. We have the vector equation of a plane, which is n dot r minus r0 equals 0. This looks a little bit strange for an equation. It's not written as a function, but it is an equation that represents all of the points on a plane. And same as before, we have r0 is this thing, and then n, the defining vector for that plane, is ABC, just like V was for the line. Parametric equations, we again split these up into components. This is not as obvious, but you need two parameters here, T and S, in order to get all of the points on a plane. It's a two-dimensional surface, therefore you need two parameters to write it down. The scalar equation looks like this, which is probably what you're more familiar with. Which just have x, y, and z. You say, all right, that's equal to 0. And then you have the linear equation, which is a variation of this guy. All right. Next, we have how do you write down these formulas? Well, given some points, P1 and P2, or P1, P2, P3, you can use these tables to figure out, okay, what are all of the things that I need to write down the equation of my line or my plane? So given points P1 and P2, you just choose one of them to be R0, your starting point, and then V will be the difference between those 2 points, because if they're on the line, then all of the points in between them should be on the line, and thus the vector pointing from one to the other should be on the line. And then that's your V, and you write down the vector equation, or the vector formula. For a plane, you're given 3 points, because you need 3 to specify a plane. And then you choose one of them to be your R0. And here, you need 2 different vectors, so U and V. And hopefully your points P1, 2, and 3 are not collinear. So if they're all in the same plane, but not on the same line, then you pick, right, your R0, your starting point, and you pick the vector going from R0 to one of the other 2 points. For U, you could pick P2 and V P3. If you pick P2 for R0, then you can pick P3 minus P2 for U and P1 minus P2 for V. Notice that the starting point is always subtracted off for the vector here. All right, and then once you have those parameters, you can get your normal vector by taking the cross product. Remember that if you have 2 vectors U and V, then the normal vector will be perpendicular orthogonal to both of them. And that is why when I have this, r minus r0, so any vector in the plane, you dot it with that normal vector, it should be 0, and that's what it means to be orthogonal. All right, last is the distance from a point P to a plane, pi, and I'm just going to give you the formula here. It is not super obvious why that formula works, and that will show up in the explanations video. Okay, so those are our formulas. Next up, we have our objectives. They are reasonably short. So easy ones, you should know at least one of these equations for a line, one of the equations for a plane. And last easy one, you should be able to write down the equation of a line or a plane given those points. So use this table or some method that works for you. All right, and then the medium objectives here, you should know several ways each of specifying lines and planes, and you should be able to translate between them. So given, say, the parametric equations for a plane, you should be able to take those and turn them into a vector equation for the plane, or a scalar equation for the plane. Or if you're given the symmetric equations for a line, you should be able to take those and turn them into the convex equation for a line, or a convex equation for a line. That's what I mean by translate between equations. Last, you should be able to compute distances between points and lines and planes, blah, 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 using this formula right here. This can take a little bit of creativity. We'll see that in an example at the end, or at the end of the examples video. And then our one hard objective, you should be able to derive all of these equations by considering geometric situations. So I'll show you on the next page some pictures, and you should be able to draw similar pictures yourself after mastering this section and figure out, okay, that's why I have to write down this for the vector equation of a plane, or this for the convex equation of a line. Okay, next up, let's cover all of those terms a little bit more in depth. So first off, we'll look at the vector equation of lines and planes. So here we have our 3D coordinate system, and we have a line L and a plane pi, capital pi right there. And what I've done is I've drawn some points on L and said, all right, those points correspond to values of the vector function R at different parameters T1 and T2. And if I pick T1 as my starting value, I get R0 right here. And I take the difference of these two values of R, or the difference between these 2 points Q and P, and I get my vector V. Okay, and then that I can write down in my vector equation format. And so what's happening here is I'm saying, all right, I start here, and then I add the vector V. Well, that gives me exactly this vector pointing from the origin, the start of this vector, to the point Q, the end of the vector V. And then if I add twice V, well, I add more over there. And that's why this parameter T is here, because it scales how much of V you add on, which scales you directly along the line L. Okay. Next, we have the plane. And here's what's going on here. So we have several points on the plane, all given by different values of those parameters T and S. I've called them alpha, beta, and gamma. And then we can use those points to find the vectors U and V. And then remember, our right-hand rule says cross U and V. So go from U to V using your fingers. Your thumb points up that way in the direction of N. Now, when you find this vector N, it doesn't actually matter which way you cross U and V. You just need something orthogonal to both of the vectors U and V. I could have done V cross U and chosen that to be my normal vector. But to be consistent with my teaching, I put U and V. Okay. And then so once you get that, you remember, oh, well, this is orthogonal, those little right angles there. And that means that the dot product of N with any other vector in this plane, and I mean in the plane, so parallel to U, parallel to V, or somewhere linear combination of the two, must be or must have a dot product of 0 with n. All right. And then here we have the vector equation for a plane. All right. So now what is a parameter? Well, you write down one of these vector equations or a parametric equation, and you get t's and s's. And these things are variables that don't really show up in the graph anywhere, but they are used as a way of tracing things out, specifying specific points without corresponding directly to x, y, or z. All right, so a parametric equation is any equation involving parameters, like the t and s, usually not represented explicitly. So if you write out the components of r, x, y, and z in their formulas using t, this is a set of 3 parametric equations in t. All right, direction numbers we have for a line, there are the components of the vector v, a, b, and c. Those are your direction numbers. For a plane, your direction numbers can be given in 2 ways, one by the normal vector or by the components of 2 different non-parallel vectors in the plane. So u and v here. Symmetric equations, we only have these for lines. You can get them for a plane, but they are much more difficult. And so I'll leave that as maybe a challenge problem. But for now, we have these symmetric equations, and they're called symmetric equations just because they look the same. If you were to swap all the x's, y's, and b's, things would look more or less the same form. Variable minus constant divide by constant. And these are the direction numbers, note. A, B, and C tell you what slope the line is going in each direction, x, y, or z. If one of these slopes is 0, so you're parallel to the z xy plane, then you have z equal to some constant number, and c is 0. So you just write this as a second equation, and you don't have a fully symmetric set of equations. You only have symmetry in x and y, and then z is off to the side right there. All right. Convex equations are a way of controlling where the parameter t starts and ends. So they're written in this format. Why is it this format? Well, okay, we specify values of t from 0 to 1. And this helps us understand a little bit better why we do that, or why we do this form for the equation. Because now, if t is equal to 0, well, then 0 times q is 0, and 1 minus 0 is 1, and I'm just left with r equals p. If t equals 1, similarly, this term vanishes, and I get just q right there, so r equals q. So when t equals 0, I have a vector pointing to that point on the plane, the one that I wanted to start with, and when t equals 1, I have a vector pointing to the point that I wanted to end with, q. So it's a way of normalizing the parameterization t. The normal vector to a plane is any vector n satisfying this property. And that is exactly why we have this formula for the equation of a plane, and that's our normal vector right there. Notice it says any vector. It does not have to be a specific vector. And there, I should have written that. Yeah, any vector at all will work, as long as it's orthogonal to all of the vectors v in the plane. All right, the scalar equation of a plane. Well, you take this dot product and you multiply it out. So here we have n r minus r0 as our left side of the equation of a plane. And then we just write out the components and multiply everything out. And that's still equal to 0. So this now is the scalar equation. Next up is the linear equation. It doesn't really need a different name, but this is basically take this equation, multiply A, B, and C in, and then bring all of the constants to one part of the equation and the variables to the other. So now you have something that looks a little bit cleaner. Note that I do have the D constant on the left side with the variables. This will be important later on for that distance formula, because if we look back at that, notice that this looks like, there's the D part right there, and that D needs to be the correct sign. Otherwise, I can get the wrong value for the distance between a point and the plane. Okay, so that is our overview of section 1.5. In the next video, we will cover some examples of computing equations of lines and planes.